Okay, welcome to Unit 6, and today we're going to start our unit by looking at something called Antidifferentiation. You're like, what? We just did a whole bunch of differentiation. That was like the whole course up to now. Yes, now we want to go the anti way. So what's that mean usually when you put an anti in front of a word? Yeah, perhaps the opposite. And so that will be a key indication of what we're going to be doing today. And then we'll introduce to you this term called indefinite integrals as well. Okay? Now, as a warm-up, can you please differentiate these three examples? And yes, they're not meant to be difficult, so don't be afraid that the answer is pretty straightforward. Using the power rule, yep, you get 3x squared. For number 2, yes, 3x squared. Now, the derivative of negative 10 is 0, so you can put plus 0 if you want, but really plus 0 is the same thing as not having it there. So what if I change it to any constant? Well, like you should have remembered, the derivative of any constant is really just 0. And so can you see how each of these three different functions have the exact same derivative? So now if I ask you, what do you think we should get when we anti-differentiate? And if you think about what anti-differentiate means undo the differentiation, or the opposite of it. Well, if I started with 3x squared, then if I were to go back, I should get what I'll be getting with. So f of x equals to x cubed. But once again, the question is, what's my constant? Is it, like example 1, 0? Is it negative 10? Or is it just any number c? Well, hopefully you can see that it should be just any constant number c. Now, this whole idea of anti-differentiate, that can be written as the following. Now, we have this new symbol, okay? This squiggly line, or sometimes people call the snake, is really this symbol called the integral, okay? This is the integral symbol. So the idea is it's telling you to integrate, or another word for integrate, once again, is anti-differentiate, which means the opposite of derivative. The expression that follows it. So what we're really saying here is this is the integral of the function 3x squared, and then there's something called dx, okay? And that dx is an indicator that you are integrating with respect to the variable x, okay? Now I've highlighted these pieces, so once again the integral symbol is this thing that looks like a snake. The expression, which we call the integrand, is the one in green, and that dx is a notation that shows you're integrating with respect to x. Okay. Now, whenever you do these indefinite integrals, you're always going to get this plus c. Plus c is called the constant of integration, and it has to be written as part of your answer because, like in the first examples here with the warm-ups, we don't know what that constant will be. Okay, so how do we actually go about doing an antiderivative, or aka the integral? Well, here are some integration rules. Just like we had a power rule, which we had for derivatives, we have a power rule for the integral. Remember, for the derivative, we took the exponent, we brought it down to the front, and we reduced the exponent by 1. Well, what's the opposite process? Well, the opposite process is to increase the exponent by 1, right? Increase the exponent by 1, and that's why you have this x to the power n plus 1. And instead of multiplying, we're now going to then divide by, so divide by the new exponent. So we're dividing by n plus 1. And then don't forget, once again, a plus c at the end. Okay? We have constant rules too, so if it's a constant, the antiderivative of a constant is really just a linear function. So think about that, right? How we had, when we were talking about the slope of the derivative, we're going backwards. So a derivative of a linear function gives us just a constant. So when I do the antiderivative, or the integral of a constant gives me a linear function, a constant times x plus c. Okay? Now, you can also use the power rule. Remember, a constant times x to the power 0. You can do that as well. So when I integrate that, we have what? X to the power of 1 over 1, and you still have that constant in front, right? So kx, and then don't forget plus c. Here I just tried to show you what happens when you have a scalar multiple in front. If you have a scalar multiple in front of the function, don't worry about it, okay? Take it out, ignore it, and just do the integral of the actual function, and then just apply the constant back in, okay? So key thing here is the constants may be factored out of the integral expression, but please, please, please never factor out a variable. So if there is a variable, you have to leave it inside. You cannot take out and put it in front of the integral sign. Okay? And similarly, the sum and difference rule we have for derivatives also apply to integrals. So the integral of a sum is just the integral of the individual pieces then added together. Okay? All right, let's try these then. Here are some examples. We're doing some skills again. Okay? The integral of x cubed dx. So remember, the idea is this integral and this dx are together, and once we do the integral, those things disappear. So when I do this now, the antiderivative of x cubed, I'll use the power rule, which means I should increase the exponent by 1. So 3 plus 1 is 4. Then I'll divide by the new exponent, and then don't forget plus c. And once again, once you've done this, that integral symbol, that dx, those disappear. Okay. All right, how about the next one? This is the integral of a constant too. Well, then the integral of a constant is just a linear function, so that'll just be 2x. And then don't forget, plus c. Thank you. There's always going to be a plus c at the end for these indefinite integrals. Number 6, I think I should separate. So think about doing them as two separate things and putting them together. So the antiderivative of t to the power of 4. Now you see how this is t and this is t. So we know that's the variable we're using. That's why we have this notation. So we will then increase the exponent by 1. We'll divide by the new exponent. So that's the first piece. And then how about that plus 2? Yeah, that just becomes, it's a constant. So a constant's integral becomes a linear function, 2 times t. And don't forget plus c. Okay? All right, let's keep going. Number 7. 3 things. Not a problem. We'll just integrate each of them individually. Ooh, this one has a 2 in front. So really what you could do is just ignore the 2. And I can say, let's just integrate y squared. Okay, dy. By the way, for this one, I'm just going to separate it so you can see what I can actually do with the sum rule as well. I can then say, hey, there's a 4 here. I can take it out in front. The integral of y dy. And then finally, the integral of 1 dy. Now, you don't need to write this down, but if you want to see the individual pieces of how I'm doing this is fine. Many people will just skip to our next line right away from the first piece. Okay. How do we do that? Well, what's the integral of y squared? We're going to add 1 to the exponent, divide by the new exponent, and then don't forget we still have the 2 in front. Okay. We're not going to put a plus c here yet because we're really going to put a plus c everywhere, and we don't need 3 plus c's. We just need 1 constant to represent all the constants together. So we'll just do that at the end. Okay, the next one, integration of y. That becomes y squared over 2. I guess we still have the 4 in front. And then the integration of 1 dy, that's of course just a linear function y. And then now we can put the plus c. Okay. Similarly, now you can simplify, so 2/3 y cubed. 4 divided by 2 is just 2y squared plus y plus c. There you have it. Okay. So once again, just try to change everything into power rule, and then you can just apply power rule to all these pieces. I'm thinking that would be good advice for number 8, because it'd be nice if we can change all that into a power. So 3. This is x to the negative 2, and then minus, this is x to the square root, yeah, it's half, it's in the denominator, so negative powers. So if you rewrite this as a power, I think it's much simpler for us to actually do the integral, or the antiderivative. And so here we go. We will take the antiderivative of 3x to the negative 2, so 3 is a constant, I'll just ignore. I will once again add 1 to the exponent, so that becomes negative 1. Divide by the new exponent. And then for the next term here, once again add 1 to the exponent. So let's think about this. Negative 1/2 plus 1 is? Yeah, 1/2. And then we have to divide by 1/2. And then don't forget plus c. Hopefully you can now make this a little bit nicer. We will simplify. Negative 3x to negative 1. Dividing by 1/2, same thing as multiplying by 2. Or if you want to write this as negative 3 over x minus 2 root x plus c, that is perfectly fine as well. Depending on what your teacher wants, this is good, this is also good. Okay. Now see if you do number 9 on yourself. Okay, so same like number 8. Simplify first into a power and then do the antiderivative. Press pause. So I would rewrite this. Hopefully you can see that I can separate it. I would still try to simplify first. The root x over x squared, write it as a power. I think that's x to the power of negative 3 over 2. That's x to the negative 2. And now, once I have it in power form, we're ready to anti-differentiate. Using the power rule, we'll add 1 to the exponent, divide by the new exponent. Don't forget your plus c. And once again, once you do this step, notice the integral and the dx, they disappear. We simplify. And I think this is good enough for me. Is this what you got? If it is, give yourself a pat on the back. Yay! Alright, now as we turn the page, just a quick note. Once again, we always need the plus c when you do the integration. Don't forget, we never have a plus c when you differentiate. Okay? Now, you're thinking, okay, do all answers have plus c? Well, yes, but if I give you some sort of initial condition or some extra piece of information, which then allows you to hopefully solve for c. So remember our original example here where I gave you the derivative. I think f prime of x was 3x squared. And then I said, hey, f of x equals to x cubed plus c. So the idea of that is, yes, you get the x cubed graph, and it could be this one, it could be this one, it could be this one, it could be any of these. So which one do I actually choose? Well, now with an initial condition, let's say I said, hey, we're going to take the one that goes through this point. Well, then I know this is the particular graph I want. And so using this idea now, we should be able to solve for c. So looking at example number 10, if f prime is equal to x to the negative 3, and I have this initial condition here, right? F of 1 equals 3 halves, I should be able to find f of x without having the plus c there. Well, how would I do that? Well, first of all, I got to find f of x, which is really just the integral of x to the negative 3 dx. We quickly do this using the power rule. And yes, we have a plus c so far. I have negative 1 over 2x squared, then plus c. That's what we got so far. But now, since we know that f of 1 equals 3 over 2, I can plug that in. 3 over 2 is my y value, so 3 over 2 equals to negative 1 over 2, and our x value here is 1. And now we should be able to solve for c. 3 over 2, negative 1 half. We'll add 1 half to both sides. 3 halves plus 1 half is 4 halves, which is equal to 2. So c equals to 2, and therefore now we know f of x is not just negative 1 over 2x squared plus c, but we know the actual corresponding value of c, and that would be 2. And so when you're given an initial condition, we can now eliminate the c and figure it out. Okay. All right. Let's look at 11. 11 is kind of funky. You're like, what does this mean? Well, we have this ddx. That means, that's right, differentiate. It says differentiate the, and you're like, what's this thing? The integral and dx. That would be the antiderivative, or anti-differentiate. So we're going to anti-differentiate a function and then differentiate it back. What do you think we're going to get? Well, I'll let you think about this one. Anti-differentiate, then differentiate. Aren't they the opposite operations? You bet. So shouldn't I just get what I started with? You bet. So you would just have 5 root x minus 1 over x squared. That's it. Now you don't believe me? Go ahead. why don't you go and rewrite this as a power, take the antiderivative of it, and then get the result, blah, 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 and then take the derivative of that. And guess what you're going to get? You should get that. But I'll leave that up to you for exercise. All right. How can we quickly apply this stuff? Hey, remember those acceleration, position, velocity, all those type of questions? Yeah, so if you know the acceleration equation for object, and you're given an initial condition for the object's velocity and position, guess what? Integration, or the antidifferentiation process, allows us to find the velocity and position equations. So position, velocity, acceleration, yeah, differentiate. Going backwards, acceleration to velocity, velocity position, yeah, you integrate. So in this case, I've got an acceleration particle. It's given by this function, a of t equals to 4t minus 3. How will we find the velocity? Well, the velocity, once again, is the integral of the acceleration function, which would just be the integral of 4t minus 3 dt. And if we quickly do that integral, I think, yes, you get 2t squared minus 3t, and don't forget, plus c. But wait, we have an initial condition, so we should be able to solve for c. The velocity is equal to 6, when the time is equal to 1. And doing this, we shall see 6 equals to 2 minus 3 plus c. c must equal to 7. And so therefore, we now know the velocity equation is 2t squared minus 3t plus 7. And then now if I ask you to find the position, I just want you to take the integral of velocity. So I'm going to actually ask you to do this and see if you can come up with the actual integral and then figure out plus c. Go! Don't forget the 2 in front. Now you can call this C again if you want, but if this is something that's different than the previous C, maybe you want to denote it with a notation like C sub 2, or if you don't want that, you can just use a different letter like D. It's up to you, okay? Once again, solve using the initial condition. D. What's this? 16 over 3. This is 6. This is 14 plus D. We can solve for D. What's that? Negative 3 minus 16 over 3, I think. And that just becomes negative 25 over 3. That's D. And therefore, we now know our position equation is 2/3 t cubed minus 3/2 t squared plus 7t minus 25 over 3. Cool. All right, one last example. This one you might have seen from physics. Given that on Earth the acceleration of an object is 32 feet per second squared. We're putting a negative in front because it indicates a downward development. But those of you in Canada, how about negative 9.8, right? Meters per second squared. And if that is my acceleration, can you figure out the equation for the velocity of the object? And also using this v naught as the initial velocity, so that means at time t equals to 0, our velocity is this v naught. And then also do the same thing and find the equation for the position of the object, and then use this as our initial condition. Okay? I don't think I need to do this with you, because it's pretty much the same thing, example number 12. So once again, you try, and then come back and check. Okay? Press pause right now, please, and do the work yourself. integrating this, t squared over 2, don't forget we have negative 32 in front, v0t, plus, and I'm going to use c sub 2 this time, okay, you can use that or d, doesn't matter. Then I'm going to plug in my initial position, thank goodness t is 0, that makes life so much easier. c2 is equal to s0, so therefore s of t equals to negative 16 t squared plus v0t plus s0. And those of you in Canada, instead of having negative 32, you should have negative 9.8 t plus v0. And then instead of having that, it's half of negative 9.8, so negative 4.9 t squared plus v0t plus s sub 0. Alright, there you go. Welcome to antidifferentiation and integral calculus.